Welcome back to Statistics. In Chapter 6, we will be dealing with continuous random variables, and there are three main probability distributions that we will be discussing, namely uniform, normal, and exponential. Let's first define what are continuous random variables. In Chapter 5, we dealt with discrete random variables, and as you will remember, those variables can take on values that are round numbers. In contrast, continuous random variables can assume any value in an interval. Hence, it is not possible to talk about the probability of a continuous random variable assuming an exact number. So for instance, we cannot say what is the probability that the average height is 68 inches or 69.3 inches for that matter. Instead, we talk about the probability of the random variable assuming a value within a given interval. This notion is important. Interval. For instance, there is an X% probability that the average height is between 65.2 inches and 71.1 inches. Something like that. The key thing there is that you have to think of an interval. Now, what is the probability, therefore, of a continuous random variable falling between two numbers or falling within an interval? It's simply the area of the graph under the probability density function. What then is the probability density function? Remember the histograms in Chapter 3, which depicted the probabilities of each possible number? In that case, the histograms look like bars. But in this case, because the variables are continuous, the histograms will look like smooth lines. Now the area under the line will always be equal to 1 because it will cover all probabilities. And therefore the probability of any range of numbers will just be the area or the proportion of 1 that is covered. Here is a concrete example. Consider the uniform probability distribution. For instance, think of a random variable that ranges from, say, 0 to 6. So its smallest value is 0 and its largest value is 6. And assume that the probabilities are uniformly distributed. In that case, the probability of any interval will just be proportional to the interval's length. And here are the formulas for the expected value of the continuous random variable as well as its variance. For instance, here, Slater's customers are charged for the amount of salad they take. Now the amount of salad they take is uniformly distributed and ranges from 5 ounces to 15 ounces. Hence the smallest value is 5 and the largest value is 15. This is therefore the probability distribution of the salad filling weight. Hence, its expected value will be 10 and its variance will be 8.33, where we just plug in 15 and 5 into the relevant formulas. And this is the probability distribution depicted graphically. So what is the probability that a customer will take between 12 and 15 ounces of salad? All we do is consider that the distance is from 5 to 15 and the distance from 12 to 15 is approximately 1/10 of the whole distance of 5 over 15. Hence, the probability will be equal to 0.3. So, this is what you should take note, that the area under the graph and the probability are identical. Hence, if you can measure physically the area under the graph, you can measure the probability of the number falling within that interval. But there's no need to do that physically, because there are formulas that we can use for estimating the probability of continuous random variables. We now move to the normal probability distribution. I strongly urge you to study this intensively, because we will be using this very much, and it's going to be the foundation for hypothesis testing and the other concepts we will be discussing in chapters 7 to 11. It is widely used in statistical inference, and it applies for a wide range of phenomena, such as heights of people, rainfall amounts, test scores, etc. So please take a moment to perhaps review your PowerPoint and also review your textbook, and we will then proceed with the normal probability distribution.